In this tutorial, we're going to look at methods for two-sample proportion inference. Again, we're going to look at the CHIS Health Disparities dataset, and this time we're going to look for an association between poverty level and whether or not you visited the doctor in the last 12 months. To do this, we're going to look at a two-sample test of proportions using a normal approximation to the binomial distribution. So the first thing I want to think about is, how can we define a test statistic for comparing two proportions? We looked at contingency tables in class, but now we're going to look at how we might define a test statistic that looks something like the two-sample t-test that we saw last week. So we're interested in, let's say we have x1 that follows a binomial distribution, sample size n1, proportion p1. And let's say that these are the people who are below the federal poverty line. There's n1 of them with probability of visiting the doctor p1. Now we have those who are not below the federal poverty level. All right, and again, we have a sample size and a proportion, and we're interested in testing whether or not those two proportions are equal. All right, so the first thing I want to do is think back to when we did the two-sample t-test for equal variances. In that case, we had some variable x1 that followed a normal distribution with mean equal to mu1 and variance sigma squared, and another group. And note that those have the same variances because I'm only interested in the case where we're assuming equal variances. And we'll get into why that is. So recall we constructed a test statistic that looked like t is equal to the sample mean in group 1 minus the sample mean in the other group divided by a pooled estimate of the variance times the square root of 1 over n1 plus 1 over n2. I misspoke there. This is a pooled estimate of the standard deviation. And this guy, under the null hypothesis, followed a t-distribution with n1 plus n2 minus 2 degrees of freedom. And recall, I forgot to state this, but we were interested in the hypothesis that mu1 equals mu2. The alternative is that mu1 is not equal to mu2. Okay, so what I want you to see here is that we're dealing with a very similar structure of a problem. You know, we're comparing two groups. When we had normally distributed data, we used this t-distribution. However, since we're looking at a large sample inference problem here, we're using the normal approximation to the binomial, we can again come up with a test statistic that is normally distributed. All right, so let's look briefly at how we might construct a similar test statistic. We have the sample proportions, let's call them p1 hat, which is equal to x1 over n, and then we have p2 hat, or p0 hat, which is equal to x0 over n0. This is an n1. So now we can come up with a test statistic that looks very similar. We can do the sample means, p hat 1 minus p hat 0, divided by, and then what are we going to put in the denominator here? Again, we're going to want a pooled estimate of the variance. So if we think back to the normal case, for normally distributed data, we know that these standard deviations, they're actually independent of the mean. However, in the binomial case, the standard deviation of the random variable depends completely on the mean. So that's one huge difference between binomially distributed data and normally distributed data. Obviously, there are other differences. So what we want down here in the denominator is we want an estimate of the pooled variance under the null hypothesis. So the key thing here is that we calculate our test statistic under the null hypothesis. Consequently, under the null hypothesis, we know that P0 is equal to P1. So we need to come up with some pooled estimate of the variance. We know that the variance of a binomial is P times 1 minus P. So we just need to know what is this pooled estimate of P under the null hypothesis. And that's actually very easy to calculate. We just sum up x1 plus x2 divided by n1 plus n2. And then again, we need to multiply by the 1 over the sample size in group 1 plus 1 over the sample size in group 2. And then under the null hypothesis, making the large sample assumptions, we know that z follows a standard normal distribution. We don't need to use the t-distribution in this setting because we're assuming that we have a sufficiently large sample size. Remember, asymptotically, the t-distribution is equivalent to the normal distribution. So we're using asymptotics here, and the t-distribution only works for data that's originally normally distributed. So For our binomial data, we're using this asymptotic result, and we have this test statistic that follows a standard normal distribution. But you can see that the structure is very similar. We have our difference in means up here. We have our pooled estimate of the standard deviation, and then you have this fraction that takes into account the sample size in each of the groups. Now let's go ahead and see how to actually do this two-sample proportion test in Stata. So open the CHIS Health Disparities Dataset in Stata. We're interested, remember, in testing the null hypothesis that P1 equals P0 versus the alternative that they're not equal. We're going to do this at the alpha equals 0.05 level of significance. Let's go ahead and do the hypothesis test, and we also want to report a 95% confidence interval along with this hypothesis test. Now, before conducting a large sample test, we need to make sure that the normality assumption is appropriate. We can first tabulate our data. So the first thing we want to do is we want to calculate P. We can do that from this tabulate right here. We want to look at the people who went to the doctor. So X1 is 358. We got plus 44 divided by the total sample sizes that are above and below the poverty line, 437 plus 63. We perform that calculation in Stata, and we find that the estimate of the pooled proportion is 80.4. So that's under the null hypothesis that P1 and P2 are equal. If you remember from the previous tutorial, we also could have just run the command tabulate doctor. And so what this is, when we don't stratify by doctor, it just pools the two groups together, and we find the same estimate of the pooled proportion. So for now, for those who are below the poverty line, I can check the normality assumption. I would do 63 times 0.804, and I would do 63 times 1 minus 0.804. And I find that these numbers are about 50.7 and 12.3. These are obviously both greater than 5. So I know that the normality assumption works for my group that's below the poverty line. Now I can look at this and see that for those above the poverty line, my sample size is much larger than 63. So I know that normality is going to work for that group too. So I say, okay, I can go ahead and use these large sample procedures. So to do this test in Stata, we're going to go statistics, summaries, tables, and tests, classical tests of hypotheses. Then we're going to go down and we're going to do a two-group proportion test. Our variable name, our outcome, remember, is doctor. Our group variable name is poverty. Then we can hit submit. So again, we use the same PR test that we used in the past tutorial. This is the large sample test for proportions in Stata. The output gives us a lot of good information. It gives us information for above poverty line, below poverty line, gives you the mean, as well as a confidence interval. And it also gives you the mean and confidence interval for the difference in proportions. For the hypothesis test, we would want to know the test statistic, which is Z. It's equal to about 2.3. We know that under the null hypothesis, that Z follows a normal 0-1 distribution, the standard normal. And we can go down here and we find that our two-sided p-value at the 0.05 level is 0.024. Therefore, we're going to reject the null hypothesis, and we conclude, based on the two-sample test of proportion, that there's evidence in the data that individuals in California who are below the poverty line are less likely to go to the doctor. And how do I know that they're less likely to go to the doctor? I can come here and I look at this estimate of the difference between the two groups, and it tells me, Stata says, the difference that I calculated, I did the proportion above the poverty line versus those below the poverty line. So I see that there are more people, I can also look at these numbers up here, there are more people above the poverty line that are going to the doctor every 12 months. The last thing that I want to look at in this tutorial is, let's consider the following situation. We look at these data, we say, okay, it looks like people below poverty are not going to the doctor as frequently. So I'm going to go and conduct an intervention to see if I can raise that rate among those below the poverty line. I'm going to randomize individuals to intervention or no intervention to try to see if my intervention's working. I'm designing a study. And now I need to think, okay, well, how many people do I need in this study? I decide I want to power my study to detect a 15% risk difference with 90% power, assuming that the proportion in the no intervention group would equal the estimated proportion among those below poverty in our sample that we've observed. Using this scenario, what sample size would I need, assuming I'm going to have equal numbers of individuals on intervention versus no intervention? So this is getting at the idea of sample size calculations for a binomial outcome. To do this in Stata, we're going to go statistics, power and sample size, and then go to tests of means and proportions. We're using this exact same SampSci command that we used before when we had normally distributed data and we wanted to do a comparison of means. I'm going to skip down and I'm going to look at this two-sample comparison of proportions. All right, so using the information I have, remember I wanted to use the same sample proportion that I saw in this data. So in group 1, let's just round it. Let's say that for the no intervention group, we would expect to see a proportion of 0.7. Remember, we're looking for a 15% risk difference. So in the group with the intervention, we would expect to see a rate of 85%. All right, and let's look at the options. We wanted to compute the sample size. The power of my test was supposed to be 90%. That's the default. And we want to do a two-sided test. I run this command, and you can see that my required sample sizes are I would need 174 people in each group. Therefore, to conduct my study, I would need to recruit 348 individuals. So we found that we need a sample size of 174 in each of these groups, which means we need a total sample size of 348 to conduct our study. Note that I forgot to mention in the problem statement that we did want to conduct our tests comparing intervention versus no intervention at the alpha equals 0.05 level, the standard level that's used in most analyses.